This is topic 2, Introduction to Mathematical Programming, Part 2, Multivariate Optimization, and this will be Part A. In this section we consider a problem where there are two decision variables, x1 and x2. In Part 1 we looked at a problem where there was just one decision variable, we'll find there's much that's familiar when we look at a problem with two decision variables, but some things are slightly more complicated, and because of this then we just restrict ourselves to looking at a problem with two variables. So the first step is to actually use Mathematica to define a two variable function, and the function we're going to set up we'll call profit var, and it's got two variables, x1 and x2, and the function has got this quadratic form, and you'll notice that there's an interaction term there between x1 and x2, and there's a linear term in x1, and then there's a squared term there. So a relatively simple function, and from now on we're going to use the abbreviation that this function is given by x1, x2, otherwise the notation becomes a little bit difficult. To get some orientation, then I use nmaximize, which we used in the univariate problem. So all I need to do for this is just to plug the function in there. So profit var with the two variables, say that we want to optimize over x1 and x2, and it gives back an optimal solution, we hope. And the optimal profit level is 108, the optimal value for x1 is 12, the optimal value for x2 is 6. So that's a solution. Alright, now in fact that's what we aim to do. The rest is really explaining how the computer does this and on what underlies optimization when we've got two variables. When we want to start looking at a problem, pretty well any mathematical problem, then the thing to do is to plot it. Plotting is a bit more complicated in that we've got two variables, so what we have to do is to use a command called plot 3D. Plug the function in there, say that we want the values of x1 and x2 to go from 0 to 20. Then put in some stuff about the formatting of labels. We've also put in a plane to accompany this graph, and we've also identified the optimal solution, which is actually this one here, where x1 is equal to 12. And if I project over into there, I suppose it's very difficult if I project it in the wrong direction, then x2 is equal to 6. So that's the optimal solution. I'm going to get rid of that one because that's rubbish. Okay, so x2 is equal to 6, x1 is equal to 12. The plane just touches the function at the optimal solution, and you can think about that as being the two-dimensional version of a tangent. So in the case of a univariate problem, then we had tangent lines which indicate the slope of the curve, and then when we have the stationary point where the objective function is maximized, then the tangent is horizontal. With a two variable problem, then actually this plane is horizontal.